Hi, my name is Jeremy Piangmeth. I'm a partner with Orange Line Studio. We're a strategic design and education planning firm, and we focus a lot on projects in sustainability and renewable energy. My career in the fields of architecture and construction management have prepared me to take on this really interesting project that I'm going to share with you today. We were approached by a client in New York City who wanted to find out whether or not it was feasible to put wind turbines on a building. This potential project was in the northwest section of Manhattan, only a few blocks from the Hudson River. Here you see the site location and the building taking up almost a full city block. So there was plenty of roof space for wind turbines. We knew solar power wouldn't work because adjacent tall buildings block the sun to the roof. But would there be enough wind flowing over this rooftop to produce wind power? The question was, could wind turbines on the roof of the building actually catch enough wind? Could such a project work? In order to solve our problem, we had to understand three main sets of constraints. First, we had to understand what is wind energy and how does it work? We also needed to know how does a wind turbine work? And finally, we had to analyze how does wind actually interact with the building site? Let's start with understanding how wind works. Wind is a fluid. Wind bubbles and moves around objects. It eddies like a stream. It travels between mountain passes, and it can curl around buildings within cities and can create geographically specific wind currents. Up high, with nothing in the way, the wind travels in a straighter line, but when obstacles are present, how do you predict which way the wind will move? How do you make wind movement work for you? Wind in dense urban areas presents a particular challenge. Buildings get in the way of wind, but they can also funnel wind. The difficulty, again, is predicting the wind's path, especially because wind is not visible. In this amazing image, you can actually see the movement of the wind by the visible vapor blowing over the buildings. The next set of constraints involves understanding what kind of wind turbine would work on a building. Of course, we're not talking about the large utility-scale wind turbines you see out on wind farms. Wind turbines also come in smaller sizes, and there are different designs of wind turbines. This image introduces you to two primary types. The familiar propeller-style turbine is a horizontal axis wind turbine, or HOT. The propeller blades spin around a horizontal axis. Another design is a vertical axis wind turbine, or VOT, where the rotor spins around a vertical axis. One of the main differences in these two designs relates to how they capture wind and respond to changing wind directions. The propeller-style turbine must point directly into the flow of wind to spin, and rapidly changing wind directions will cause performance to suffer. On the other hand, the VOT, or vertical axis wind turbine, can continue to operate through changes in wind direction. The last set of constraints we needed to understand related to the specific site location. We needed to identify which were the obstructions to wind flow, or what would prevent wind from reaching our rooftop. Of course, we also needed to ask, which way is the wind usually blowing? This is known as the prevailing wind direction. For this city location, we knew the obstacles were mostly taller surrounding buildings. To learn about prevailing winds, we would be able to source some wind data from the broader New York City region. Next, we would have to determine which of the obstacles might cause the most turbulence at different spots on the roof. You can see here our building site in red, and the large hospital to the south in green. That puts the rooftop in the shade for most of the day, precluding a solar energy installation. To the west, you can see additional obstacles that will interfere with airflow and cause unpredictable turbulence at some of the locations where the wind turbines might be placed. We might expect flow from the northwest to look something like this. You can see the turbulence happening around the building and a wake being formed. You could also expect airflow to be turbulent in vertical directions as well, as wind has to move over obstacles and will curl back into a vacuum behind them. Our client wanted to figure out which of these 5 sites on the building roof would be the best for the installation of potential wind turbines. Based on the information we've just presented, which of the 5 sites do you think is best for a wind turbine location? Don't forget to consider the local prevailing wind directions, the complexities of wind in urban areas, and the local obstructions to wind at each of the potential turbine locations. Here's how we approached solving this problem. We first realized that we were going to have to find a way to qualify the effects of wind on our site. So we created a 3D model of the area buildings and applied a way to visualize fluid dynamics. Computational fluid dynamics, or CFD, uses computers to perform calculations to simulate the flow of liquids or gases in an environment. Typically, you might see the CFD studies performed on 3D models of planes or cars. Through this, we would get not only data for different locations on the site, but also be able to visualize airflow for a clearer understanding of the predicted movement of the wind. We imported the 3D model and parameters needed to conduct our simulation into the CFD software. The parameters consisted of the estimated wind speeds, the variation in wind speed according to the altitude, and the surface roughness coefficients. And we ran simulations of airflow from the prevailing wind directions indicated on the windrows data that we had of the general area. In this video clip of the CFD simulation, you can see that we had taken slices of information from multiple angles and directions, reflecting the different wind directions. You can quickly see where turbulent zones happen in wakes beyond buildings. This slice is taken at only 90 feet off the street, and based on the different colors, you can see how the wind interacts with the building. Through an analysis of different slices from different directions, even vertical slices, we were able to look for updrafts, downdrafts, and understand how wind would flow at the different potential wind turbine locations. Here you can see that the wind is moving up and down with updrafts and downdrafts across the building, and that there is actually a void or lack of wind flow on the back side of the building in winds from the northwest. In order to make our decisions, we built a matrix of airflow interactions on the rooftop site and looked for the locations that would have the least turbulence and the most consistent wind speeds. First, we studied winds coming out of the southwest and noticed where on the roof they would be the most consistent. Then we looked at flow direction coming from the northwest, and we started to see an overlap offering the same level of consistency. Finally, we looked at winds coming from the west and noticed the greatest overlap happening along the ridge of the building and more toward the eastern edge. This identified site number 3 and site number 5 as the best sites. We finally chose site number 5 as the optimal location for a wind turbine array. It offered the most consistency in wind, and it offered the least amount of turbulence. It also allowed easy access for a crane to do the installation, which would be far more difficult at site number 3. We also had to recommend a wind turbine type based on the understanding that winds would often fluctuate and cause turbulence in this urban environment. We decided a vertical axis wind turbine would be more successful for this project. Again, vertical axis wind turbines can capture wind shifts instantaneously, and because they are less affected by turbulence, they also allow for more compact groupings. For this concept, we would be able to use lessons from new research to design a layout of turbines that could make the most energy possible from the least amount of space. In the end, while this project was not built, our process of applying CFD simulations proved useful for analyzing wind energy potential in urban areas. We also learned that looking for solutions in other areas of study could lead to the design of more successful projects. The research that most influenced this project and our idea to fit more wind turbines in the limited area is currently being conducted by Caltech researcher Dr. John Dabiri. Dr. Dabiri researches biomimicry, which studies how designs in nature can be imitated by technology. One area he has studied is how fish swim. Fish swim in schools, and as they swim together, they shed vortices with their tails. They stagger themselves to take advantage of these vortices, allowing them to swim more efficiently in tight formations. Dr. Dabiri noticed a synergy in the math between this and how vertical wind turbines might work, and realized that if the turbine was spaced just right in an array, the turbine array could work more efficiently as well. Since 2010, Dr. Dabiri has been conducting experiments with vertical wind turbines and has shown that with the right arrangement, the turbine array can actually produce more power in less space. Continued research to incorporate other disciplines, such as computer engineering and advanced material science, could lead to more affordable and flexible wind energy systems. Our study for a potential wind energy project involved many areas related to science and technology. It was necessary to have a clear understanding of specialties related to a variety of fields, from engineering, architecture, and urban design to computer modeling and renewable energy technology. What can you study to prepare to work with this type of project? Some of the areas you can choose to study include sustainable architecture, mechanical, electrical, and aerospace engineering, or information technologies. Programs of study can also include environmental sciences, biomimicry, advanced materials design, and even 3D modeling in geographic information systems, or GIS. I have a degree in architecture and a long background in design and construction. I also have a passion for wind and sailing and understanding renewable energy technologies. In today's world, it is very important to combine specialized studies with knowledge and inspiration from other areas. By blending your studies with your passions and observations about the world around you, you'll be able to find creative solutions to our more complex challenges facing us today.